Welcome back to OmniEyes. Today we explore the adult silkworm moth, a true master of night navigation and trajectory tracking. Unlike their younger caterpillar forms, these fully grown moths never eat. They do not even possess the functional mouth parts to feed. Surviving purely on stored energy, they have an extremely short lifespan. Every single second is critical in their urgent biological mission. Their singular purpose is reproduction. To achieve this, they must navigate through absolute darkness to locate a suitable mating partner quickly. Finding a mate in the pitch-black night is a monumental challenge. The environment is filled with visual noise and obstacles. Human eyes would be completely useless here. But the adult silkworm moth has evolved a highly specialized visual system for this. They do not look for beautiful wings or specific shapes. Their eyes are tuned to recognize something entirely different and dynamic. They are searching for a specific flight path. Their vision is perfectly optimized to detect movement patterns in the dark environment. This extraordinary ability is based on directional waves. The compound eyes process visual information as a series of moving vector lines. Imagine looking at the world not as static pictures, but as a complex matrix of arrows indicating direction and relative speed. This is exactly how the adult silkworm perceives its surroundings. It filters out stationary objects completely to focus only on movement. When another moth flies past, it creates a visual disturbance. The tracking moth instantly locks onto this sudden change in contrast. It does not care about the color of the passing object. It only cares about the trajectory and the movement speed. This biological mechanism is a perfect example of trajectory tracking. The moth calculates the future position of the target almost instantly. By following the invisible motion vectors, the male moth can intercept the female mid-air with astonishing precision and flight agility. The night sky is full of distractions. Falling leaves and swaying branches create a chaotic visual background of random background movement. Yet the silkworm moth never gets confused. Its neural pathways are hardwired to ignore random noise and focus on specific frequencies. The fluttering of a mate generates a unique rhythmic vector signature. The tracking moth recognizes this exact mathematical motion pattern perfectly. Once the target is acquired, the moth adjusts its own flight path. It constantly recalculates the vectors to maintain a lock. This continuous feedback loop happens in milliseconds. It is a highly efficient biological targeting system, operating entirely in the dark night. Scientists have spent decades studying this fascinating creature. The goal is to understand how such a tiny brain processes complex data. The secret lies in the simplicity of the algorithm. By ignoring unnecessary image details, the moth saves massive amounts of power. It only processes what is absolutely essential for survival and reproduction. This minimalist approach is incredibly inspiring for modern computer science. In the realm of human technology, we face similar challenges. Monitoring vast airspaces requires tracking countless moving objects simultaneously and accurately. Traditional radar and camera systems try to identify every single object. This requires enormous computational resources and often leads to delays. Aviation security systems are now learning from the silkworm moth. They are shifting focus from object identification to pure trajectory tracking. When monitoring a busy airport perimeter, the system does not need to know if an intruder is a bird or drone. The security system only needs to know the object flight path. It tracks the motion vector to determine any potential threat. If a trajectory indicates an unauthorized approach, alarms are triggered immediately. This saves precious seconds in critical threat response and management. Drone surveillance also benefits massively from this biological concept. Modern military and commercial drones operate in highly complex and cluttered environments. Small drones flying through urban areas need to avoid obstacles. They use motion vector tracking to navigate safely through tight spaces. Just like the moth, these drones process directional waves. They detect the relative movement of buildings and trees to avoid collisions. The camera on the drone does not analyze window shapes. It only calculates how fast the building is approaching the lens. This biological-inspired navigation allows drones to fly at high speeds. They can react to sudden changes in the environment instantly. The algorithm is lightweight and highly efficient. It requires very little battery power, copying the moth biological processing system very perfectly. Let us dive deeper into the anatomy of the moth eye. It is composed of thousands of tiny individual optical units. Each unit points in a slightly different direction. Together, they form a wide-angle dome that captures a massive field view. However, the resolution of this compound eye is incredibly low. If a moth looked at a flower, it would see blur, but resolution is not the goal here. The true power of the moth eye lies in its unbelievable temporal processing speed. Humans see the world at roughly 60 frames per second. The silkworm moth can process visual changes much faster than that. This high-speed vision allows them to see the subtle directional waves. They track the rapid wing beats of their mates. Imagine a digital camera that only records moving pixels. The static background remains completely black to save precious memory and bandwidth. When an object moves across the frame, a trail of bright pixels lights up. This is the visual world of moths. The brain of the moth connects these bright pixels to form a vector. A vector has both a direction and magnitude. By calculating the magnitude, the moth knows exactly how fast the target is moving. Direction tells it where to fly next. This pure mathematical perception of reality is breathtaking. Nature has evolved a perfect geometry engine inside the head of an insect. Engineers are currently building artificial retinas based on this exact principle. These dynamic vision sensors only report changes in light intensity. Traditional cameras capture redundant data by recording the same background over and over. Dynamic vision sensors eliminate this massive data waste. They output a continuous stream of events rather than static frames. This results in ultra-low latency and incredibly high speed. These sensors are perfect for tracking fast-moving targets. They excel in low-light conditions where traditional cameras would completely fail. A drone equipped with a dynamic vision sensor can track a bullet. It can calculate the trajectory in real time easily. This level of performance was previously impossible for small autonomous vehicles. The silkworm moth has unlocked a new era of robotics. Let us return to the dark forest where the moth flies. The male has detected a faint trace of chemical pheromones. He follows the scent plume upwind through the dense trees. But scent alone is not enough to pinpoint the exact location. As he gets closer, he switches to his visual tracking system. He scans the darkness for the specific directional wave signature. Suddenly, a moving vector appears in his peripheral vision. His brain instantly analyzes the frequency of the movement against the background. It is a perfect match. He banks sharply to the left and locks onto the trajectory of the female silkworm moth. The final approach is a high-speed aerial dance. He anticipates her movements, adjusting his own velocity to match her path. This interception requires complex spatial calculations, yet the moth performs them effortlessly, without any conscious thought or heavy cognitive processing. It is pure instinct driven by an elegant biological algorithm, a masterclass in efficiency that human engineers strive to replicate daily. The application of this technology in aviation security is revolutionary. Airports face constant threats from unauthorized drones entering restricted flight zones. Detecting a small plastic drone against a cloudy sky is difficult. Traditional radar struggles with small cross-sections and slow speeds. Optical cameras are easily blinded by the sun or heavy rain. But a system based on moth vision sees through the clutter. It looks for the unique motion vector of a drone. The spinning propellers create a distinct directional wave that stands out. Even if the drone is painted perfectly to blend in, its movement betrays it. The trajectory tracking algorithm locks on instantly. The security team receives a real-time alert with the exact flight path. They can intercept the drone before it causes harm. This proactive approach to security is essential in the modern world. We must rely on smart algorithms rather than raw computing power. Beyond security, this technology is transforming autonomous driving. Cars need to track pedestrians and other vehicles to navigate safely through cities. A self-driving car must predict where a child might run. It uses trajectory tracking to anticipate sudden movements on the street. By processing directional waves, the car can react faster than a human driver. This bio-inspired vision system saves countless human lives. The adult silkworm moth lives only for a few days. It does not possess a mouth, so it can never consume food. Its entire existence is dedicated to passing on its genetic code. This singular focus has driven the evolution of its incredible eyes. Every ounce of energy is channeled into the visual tracking system. It is a masterpiece of biological engineering, optimized for one task. When we study nature, we often find solutions to our most complex engineering problems. Evolution has been experimenting for millions of years. The silkworm moth teaches us that less is sometimes more. By ignoring irrelevant data, we can achieve much faster and sharper results. In a world overwhelmed by massive data, efficiency is the ultimate goal. We do not always need high-resolution images to succeed. Sometimes, all we really need is a simple motion vector, a clear trajectory to guide us through the noise and the darkness. The next time you see a moth fluttering near a light, remember its hidden power. It is not just a simple bug. It is a highly advanced autonomous drone equipped with a dynamic vision sensor. It is a marvel of the natural biological world. Researchers will continue to draw inspiration from these tiny creatures. The future of artificial intelligence is deeply intertwined with natural biological systems. We are building machines that see the world exactly like the silkworm moth. They track directional waves to navigate our complex environments. Imagine a future where city skies are filled with delivery drones. They rely on trajectory tracking to avoid catastrophic mid-air collisions. This biological algorithm ensures that thousands of drones can operate simultaneously. They will weave through the urban jungle with perfect robotic precision. The legacy of the adult silkworm moth extends far beyond its short life. Its vision system is literally shaping our technological future, from the darkest forests to the busiest international airports. Trajectory tracking is everywhere. It is a universal principle of motion and survival. As we push the boundaries of robotics, we must remain humble students of nature. Evolution has already solved the problems we face. The directional waves perceived by the moth are a hidden language of movement. We are finally learning to read this complex language. Every vector and calculated trajectory brings us closer to perfect automation. The silkworm moth provides the ultimate blueprint for machine vision systems. It reminds us that true intelligence is not about processing everything you see. It is about processing only what truly matters today. Focus and efficiency are the keys to mastering the environment. The moth demonstrates this perfectly in its desperate search for a mate. Through the darkness, it finds its path, using the mathematics of motion. It is a silent navigator guided by the flight rhythm. The incredible story of the adult silkworm moth bridges biology and advanced engineering. It shows the profound connection between life and machines. We hope this journey into the world of motion vectors has inspired you. Nature is full of these hidden technological wonders today. OmniEyes will continue to uncover the brilliant algorithms hidden in nature. We explore how animals inspire the future of human innovation. From the ocean depths to the vast night sky, life always finds a way. It adapts and evolves with absolute perfect efficiency. The trajectory tracking of the silkworm moth is just one puzzle piece. There are countless other biological secrets waiting to be discovered. Join us next time as we delve into another amazing creature. We will analyze its unique survival strategies and technological impact today. Until then, keep observing the world around you with a curious mind. Look beyond the surface and see the underlying motion vectors. You might spot a tiny moth performing complex mathematics in the dark, a true genius of the night sky flying past you. The universe is a grand design of mathematical precision and biological elegance. Every living creature plays a vital role in this symphony. Thank you for watching this deep dive into the silkworm moth vision. We appreciate your support and passion for scientific discovery. If you enjoyed this episode, please share it with fellow science enthusiasts. Together, we can spread the knowledge of bioengineering. Stay tuned for more fascinating insights into the mechanics of life. The journey of exploration never truly ends when looking closely. Remember, the most advanced technology on Earth was designed by evolution. We are copying masterpieces that have existed for millions of years. This has been another episode of OmniEyes. Thank you for joining us today, and we will see you next time.